So, let us discuss this idea of structural risk minimization, right. So, we are given samples xi and di, they are data points, di is the desired response and xi is the data point, and we want to fit the mapping, that is di is f of xi, where f is an unknown mapping, and we need to figure out this nonlinear mapping. So, let us see how using neural networks we can try doing this. We have seen that we can through algorithms, through the backpropagation algorithm or the radial basis functions or SVMs and various forms, that we can obtain these nonlinear mappings, right. So, once we get this mapping, how is the error dependent on the choice of the parameters of the network? What is the approximation error? Is there an error in the estimate, and is this estimate dependent on the number of data points and the complexity of the network? So, these are the considerations one gets into one's mind while trying to solve these problems. So, in order to study this issue, let us step by step work through the details of structural risk minimization and arrive at conclusions. So, we start with the nonlinear regression model. So, suppose we have the nonlinear regression model. We have considered this example way back in our earlier lecture, but we will reconsider it again. So, D equals f of x plus epsilon, and f is unknown, x is a data point and d is a desired response, and the desired response has noise buried inside it. Now, let us look at the ensemble average cost. So, we consider the ensemble averaged cost, and this is given by J actual as a function of f, which is expectation over all pairs x and d. This is a joint expectation, of this quantity 1/2 of d minus f of x squared. So, it is the average square error that I am averaging, and my averaging is over the joint expectation. Now, the observations inherently are noisy, but we do not have a statistical model for the noise, and we assume it is buried, and we just do this averaging over x and d. So, in order to compute the optimum value of this estimate, we know from basic statistical signal processing that this has to be the expectation of d given x, the conditional expectation of the desired response given the input. This minimizes J actual as a function of f, right. Now, I mean, how do you get this intuition? Basically, you start with the I give you data points x, and what is my best expectation, what is the best quantity. If I want to represent all my data points by a single quantity, the best way I can form my estimate is basically the mean. But now in the regression setup, this happens to be the conditional mean given that is expected value of d given x, conditional mean of the desired response given the inputs. Now f hat, and I denote star indicating it is optimal, requires the knowledge of the joint density of x and d. Which typically is difficult because a priori we do not know any parametric form of these PDFs, right. So, let us make some approximations and simplify this this issue, right. So, first thing is, let us bring in a neural network. Suppose we bring in a neural network and make a first approximation. And over what do we need to make this first approximation? So, my f of x, which is unknown, is equal to or approximately f of x parameterized by this vector w, right. It is a neural network, it can be a backpropagation algorithm based multi-layer perceptron or recurrent network or any neural network that comes into our mind. We make an approximation because we have to learn this input output mapping non-linearly, and let a neural network do this and let that function that mapping be capital F as a function of the data points x and the vector w, which is corresponding to the parameters of the neural network, right. It is not a parametric form of the regression function, but they are the buried weights of the network. Okay. Now, j of w, I can replace it, I can compute j of w as expectation, the joint expectation over the data points. Again I do the joint expectation, but instead of the unknown function f, I replace it with f of x and w, because we are employing a neural network to do this job, right. So, this is from a neural network. Now, I have parameters w that I need to arrive at optimally. So, let w star estimate be argmin over all those vectors. I mean, let us minimize this cost j of w over all possible choices of the weight vector and arrive at this optimum weight vector, which is optimum parameter set, which we call w star, right. So, all the weight vectors are buried into this vector, which is w, right. So, that is what we mean by this quantity here. So, clearly, since we are making an approximation using a neural network, though you have optimized the parameters with respect to this cost j of w, still j of w star, this is estimate, is greater than, I would put this equal to as well in case it satisfies with equality, should be greater than or equal to the error that you can get in estimating this function through the conditional mean, right. So, we can conclude this inequality, right. So, let me call this equation 1. So, we have this quantity, this inequality here. Now, this is the first level of approximation. Now, if you carefully see through this, still there is this expectation that you need to compute in this cost, right. This is over all x and d choices from this distribution from the joint PDF, right. It may be difficult because you require infinite samples to compute this expectation. Let us instead consider the time averaged energy and make this approximation further. So, consider the time averaged energy function. So, what we have is E average. So, we are looking at n points here, n and this parameter w. This is 1 upon 2n summation I equals 1 to capital N d of I minus f of xi parameterized by w. I look at this square cost. Now, the minimizer of this cost is this quantity w. I write subscript capital N indicating it is over those number of samples, hat, which is given by w n hat, which is arg min over all weight vectors or all parameters w, the time averaged energy function, right. So, what I have done here is instead of doing this expectation over the square error, the expectation is replaced by a time averaged or the empirical averaging, right, over all the examples, and that is what I have here. So, this assumes uniform distribution over the square error, right. Now, clearly when I evaluate the cost over this optimum solution w n hat that I have, I expect this error to be more than j w star hat. Maybe if n is very large, then you can say that this is greater than or equal to, and I bring in this inequality on the other side as well, right. So, what I have is j of w n hat is greater than or equal to j of W star hat is greater than or equal to J actual F hat square F hat, right. This is from the conditional mean. This is over expectation, and this is through time averaging. So, that means if I do infinite realizations, then I get this W star, because then I can do, and if I know the joint PDF, then I can do the expectation over that, and then I can compute the optimum solution. But since I do not know the optimum, I do not know the joint PDF over which I can do this expectation, I do this time averaged cost, and therefore, any estimate that I get over this time averaged cost, that should the cost function evaluated over that parameter set should be greater than or equal to the cost function evaluated over the knowledge of the joint PDF using the neural network, and this should be greater than or equal to the actual cost evaluated at F star, where F star happens to be the conditional mean, right. This is sort of conceptually clear, but what is happening in the process of going through this hierarchy of simplifications, right. So, what is practical to me is this time average cost, because I do not know the joint PDF, but I start with a neural network and I figure out my nonlinear mapping. But if I know the joint PDF, I am probably better in my approximation, but the true function that needs to be done to minimize this squared error should be the conditional mean of d given x, right. So, this is the hierarchy of simplifications. Now, because of this process, we have excess error, and excess error can be quantified as follows. This is W j evaluated at W n hat, that is the parameter set that we computed for the time averaged cost. So, this minus j actual F hat star is what I would like to compute. This is the excess error. So, this can be broken into two parts, j of W n hat. So, I add and subtract the cost at evaluated at W n W star, assuming we have the expectation. So, I do this in this form. Now, if you observe these two quantities, now this term that I underlined here is approximation error that depends upon the neural network model. So, you may get a question here in your mind that I have this universal approximation theorem, I can approximate any function, but the universal approximation theorem does not talk about the complexity. So, in practice we live with this complexity constraint. So, depending upon the complexity constraint and also the type of architecture that we consider within our neural network model, maybe it is feed forward or feedback or combinations, we are computing the optimum parameter set for the neural network that depends upon the model that we start with. That is our assumption, right. So, there is an error because of that assumption. Also, we have another error that is coming because of this deviation between j of w n hat and j of w star, and this error depends on the size of the data, that is capital N, right. If my data set is very large, then I am sort of close to my true error. If it is not, then I live with this because I have finite number of data points to play with. So, now there is a trade off between the approximation and estimation error, and that is an important important study. So, let me briefly motivate here what it is in terms of the capacity of the learning machine, right. For example, for a single layer multi-layer perceptron, this capacity of the learning machine in order to classify this or in order to give the right labels without errors, that depends largely on the size of the hidden layer, right. The capacity of the learning machine, the capacity of the learning machine largely is governed, or I would say is governed by the size of the hidden layer. Now, let us consider a family of nested approximating functions, and these nested approximating functions is given by f k, which is f x and w, that is, it depends on the data points and the parameter set, where this w belongs to the space w k, where there is a containment property such that f1 is contained in f2 is contained in f3, so on is contained in fk, where fk is a measure of the machine capacity. So, what do I mean by this machine capacity? If I endow it with a large number of parameters, etc., it is basically able to solve this problem, right. That is, the approximation error comes down, but what can happen is, because I have so many parameters as a result of my increase in the machine capacity, that I may be an overfit for the data, right, and this is a trade off that can happen. So, we will study this trade off. Okay. So, a small note here, when I mean a single layer MLP, I mean a single hidden layer. Now, Going in the sequence, so we have two components of this error, and if I plot error versus the size of the supporting functions, and here it is capital K, which is in the increasing complexity, my approximation error comes down because before the optimum point is reached, there is, let us say there is an there is this trade off. So, let me illustrate what really happens with the approximation error and the estimation error. So, the approximation error keeps coming down as a function of the complexity of the machine in terms of the machine capacity, but in terms of the estimation, after a certain point the estimation error increases because you are overfitting the data, in the sense the machine capacity is too large for the details contained in the data, right. So, this curve here which is going down corresponds to the approximation error, and this curve here which is increasing corresponds to the estimation error, and there is a sweet spot somewhere that corresponds to the optimum solution, that sort of weighs the risk between the approximation error and the estimation error, and that is the sort of trade off that we are looking for in this data modeling or the data fitting problem, right. So, just 2 points to note. Before the optimum point is reached, the machine capacity is too small for the details within the data, right. That means I need to increase my complexity, but after my optimum point is reached, the machine capacity is too large for the details within the data. That means I am sort of an overfit to this data, and therefore my estimation error sort of increases, right. So, there exists this trade off, and that is what we have to consider when we have to arrive at the optimum size of the network, right. Given the data, we have to tune our network of optimum size, so that we balance this error between approximation, balance these two errors, that is the approximation error and the estimation error. Okay. This is an important detail. So, as you design neural networks and as you decide what should be the size of the neural network, you have to consider these things into account.